Welcome to the session on masking in PQC. I hope we'll get the slides of the first talk already on the screen. Okay, thank you. So the first presentation will be by Francois Gerard, and he will talk about improving high-order mask generation of masking vector and rejection sampling in dilithium. Floor is yours.
All right, so hello everyone. This is a joint to work with Jean-Sébastien Coron, Tancred Lepoint, Mathias Ranoy, and Rina Zetoun. So I have the first talk on masking, so I can do the traditional slide introducing masking to everyone if you already know about it. So it's a countermeasure against side channel attacks. And in masking, your adversary can peek at values during the execution of the algorithm. So you assume that your adversary can get an intermediate values. You want everything to be still secure. So basically what you do is that you split your secret values or sensitive values into n shares, such that if the adversary can get n-1 value, you will know nothing about the secret value if the distributions are uniform. And so in general, we have two types of masking that we work with. One is Boolean masking, where every shares are just values such that you have to XOR them to get the sensitive value x. You have also arithmetic masking. The only difference is that now if you want to recompose your value, you have to add modulo q. Those two types of masking are useful to mask lattice-based scheme in general, because the point is that in some type of masking, some operations are easy to do, while other operations are hard to do. For example, in arithmetic masking, it's very easy to add two values, because you can just add share by share, and then you get the sum of the two sensitive values. While in Boolean masking, for example, it's very easy to do a shift. So some operations are easy in Boolean form, some operations are easy in arithmetic form, and so what you often want to do is to convert from one to the other. And in lattice-based schemes, this is what you often do. So lattice-based scheme, I just wrote the value of q for them. The gadgets, so the algorithms that are taking as input shared value, they do not change depending on the scheme. However, if your q is a bit smaller, it can be easier in practice because it can fit in a register. For example, in dilithium, you will have to deal with 32-bit shares, and so on microcontroller it can make a difference. And so in this talk, we're going to discuss techniques to mask dilithium. So dilithium now we can call it MLDSA. Also, I kept the name dilithium. I guess we have to make the switch soon. Yeah, and anyway, this is a simplified version, so it doesn't matter which one we talk about. So this is Fiat Shamir-based signature. It looks like Schnorr signature, and the only difference is that you have, you see at line 9, this rejection procedure. So if your signature does not meet certain requirements, you have to start again. And so the question is, what do we have to mask in dilithium? So I prepared this slide where I put in red what you absolutely have to mask, in green what you don't have to mask. So what you don't have to mask, it's sadly not much, but of course the output signature is public, but also the hash, the challenge from the underlying identification scheme. So you can see that at line 3 you have to sample unknowns. This is actually a value in a certain bound. Then you have to protect the nonce that is multiplied by the public parameter a, because you could try from a and y from w and a to find back y actually. The decompose operation then, which is basically an extraction of high bits, modulo q. And there is a small question about the value w1. So most people don't mask it. The thing is that during verification, you will recompute w1. So you're like, okay, it's public, then I don't have to mask it. But the thing is, maybe the w1 values for signature that will be rejected might be sensitive. To me, it's a bit unclear. I'm not going to talk much about this, but For me, there is still a discussion about that, even though most papers assume that you don't have to mask the W1 part. And then the signature, you have to protect it until it passes the rejection sampling step, of course, and the rejection sampling step, which is a verification of a bound. So you verify that in absolute values, you're above or below a certain bound at line 9. All right, so what do you have to mask in dilithium? Basically, it's this. These are the hard step to mask. So uniform sampling of a value in a range, extracting the high and low bits, compare with an absolute values, and maybe the hash function, depending on the discussion about W1. But anyway, for today, I will only speak about those 2 steps. These have been masked in the past, and we have techniques for that, but the techniques we have now are more efficient. So the first, the sampling of the nonce. So you want an arithmetic masking mod Q of a value which is between -2 to the mu to 2 to the mu. So yeah, this interval is smaller than Q. So it's not uniform sampling mod Q, it's a smaller interval in Q, and you want uniform distribution over that. The good news is that the fact that the interval is center doesn't really matter, right? Because it's easy to do subtractions in arithmetic masking. So if you get an arithmetic masking of the value between 0 and 2 to the mu -1, then you can just subtract to recenter the range. So basically, it's the same as sampling like a mu +1 value and converting to arithmetic masking. So there are tools that we already have. One of the tools we use is a fast exponential Boolean to arithmetic conversion. So from k bits Boolean to arithmetic mod 2 to the k. So it's maybe a bit fun to see fast exponential, because when I mean exponential, I'm really talking about the complexity. The thing is that, so big O complexity, it's like an asymptotic statement, right? So the thing is that it can be a problem if you go to high values, but for masking, on the other hand, you probably mask at order 2, 3, or 10 maybe, but you know, it's small values. So sometimes the complexity is not telling you the whole story. So in this case, this is actually exponential in the masking order. However, for small value, it's very, very efficient. The next tool is what we call the shift mod gadget. So the shift mod is a gadget that will take as input a masked value and output another masked value of a modulus that is shifted. So you see that the initial modulus is q shifted by k bits, so 2k to the times q, and then the output modulus is just q. So you have a shift of the modulus, but also of the value. So basically you start from a masked value, and you get as output this value shift by k bits, and the modulus is also shifted. So it's not just a conversion between two modulus, but it's also a shift at the same time. And the last thing we already introduced in the past is this modulus switch algorithm, which is where you start from modulus P1 and you go to a modulus P2 and you multiply by the ratio between those two modulus. So you can multiply each share by this ratio, and what you see is that what you obtain is actually a masked value, an arithmetic masked value in the second modulus, which is the ratio of the two values. So this is really helpful to go from one modulus to the other, but of course you have to multiply by this ratio, which is maybe not exactly what you want, but we will use this to find an efficient algorithm to do the conversion. So to do the Boolean arithmetic conversion and to sample the y, first we set a parameter to mu plus alpha. So I recall that mu is the size of the y interval, and alpha is basically log of n, so it's the log of the number of shares. So these are just the parameters that we need. Then we start from a masking of a uniform value between 0 to the mu minus 1, and this is what we have to convert. So first we use the fast exponential conversion, and now we get the masking modulo 2 to the k. So we want mod q. I recall that what we want is mod q. But okay, with this we can get mod 2 to the k, but you're already in arithmetic mask form. So the observation is the following. If those values, if the shares add to x mod q, mod 2 to the k, sorry, mod 2 to the k, it means that they are basically the value of x plus a multiple of 2 to the k by definition. And our idea is to try to extract this value delta and then to use that to recompose the value mod q. So if this holds in the integers, then it holds mod 2 to the k q. And this is where we use our first tool, which is the modulus switching. And we switch from a k-bit shift of q to an alpha shift of q. And so what we get is a masking now of the value z that we had before, but shifted by mu bits. Why mu is because if you look at the bullet 0, you see that k is mu plus alpha. And so now you have a masking mod 2 alpha q of z, which is divided by 2 to the mu. However, if you look at the value of z, z is x plus something, x plus delta time a power of 2. But x, you know by definition that it's smaller than 2 to the mu, because it's the interval we are using to sample it. So when you do this integer division, the x part will actually vanish. And what you will have is just the delta times the power of 2. And so yeah, just what I said, the z is divided by 2 to the mu, the x vanishes, and now you have a masking of delta shifted by 2 to the a, plus an error that appears because of the modulus switching, but the error is small, so everything is good. And this is modulo 2 to the alpha q. So now I use the shift mode that will shift both the modulus and the value, and now I have a masking of delta mod q. And with this, I can recompose what I want, because remember that x was the sum of the xi plus delta times 2 to the k, and this all in the integer. So now if I use the value of delta as shares mod q, I have this that holds, and so what we have is actually a masking of x mod q, which was exactly the goal. So this is the first technique we introduced in the paper, which is an efficient conversion from Boolean to arithmetic, which is independent in complexity of the modulus q. The second part was the rejection sampling. So for rejection sampling, what you want is that you want to check if you're above or below a bound, knowing that your value is bounded by another bound b. So you know that your value is not bigger than b in absolute values, and you want to know if it's below a or above a. So as an illustration, it looks like this in dilithium. So the a corresponds to the gamma 1 minus beta, and the b is the gamma 1 plus beta. So basically you have a value that will end up somewhere there, and you wonder if you're in the green part or not. So for this, the idea that we had is to first, we start by just looking at just one side of the interval, because, okay, it's absolute value, but we can just test both sides independently and then multiply the results. And so the idea is the following. You just look at your interval, and you want to know if you're between 0 and a or between a and b. For this, what you will do is shift the interval. So in the first picture, we have the interval where you start from, and the second one, we shifted everything by a. So now you have the accept value, which is below 0, so these are big values modulo q, and then you have the interval, which is just at the start between 0 and b minus a. And our idea is to divide by, ideally it would be by b minus a, such that you will collapse the reject part to 0. So if you divide by b minus a, every values that are between 0 and b minus a are sent towards 0, while the other values are sent somewhere else. And then if you have that, you can just test that you actually have if you have a 0 or not. And zero testing is something that we can do efficiently in mask form. So yeah, the only problem is that we don't know to divide by b minus a, but the good news is that you can divide by a bigger interval. Because if you divide by something bigger, surely other value will be sent to 0, but we know by definition that we cannot have values that are bigger than b. So actually what we will do is that we will divide by the first power of 2 that is bigger than the interval, so bigger than b minus a. So basically, if you put it in an equation, it's something like this. It uses the fact that if you have x minus a divided by 2 to the rho equals 0, then it means that x is bigger than a. And as I say, we have to test both sides, but for this it's easy. You test for x, you test for minus x, you multiply, and if you have something different for 0, you know that you're in the right interval. So to summarize these as steps, you start with the masking mod Q, and then the first step that I will not explain in details is that you use a technique basically like before with the modulus switching to get the masking of x mod a shift of Q, so 2 to the rho minus Q. And then you can just compute minus a. It's easy to subtract in arithmetic mask form for both sides. And once you have that, you order multiply everything, and then you test at the end if you have a 0 or not. So yeah, this nice technique is it's actually very efficient. There is just one last thing about this is the no abort versus early abort discussion. So the question is, so in dilithium you have to test a vector of values. It's not just one. And so you will test them one by one. But in the unmasked version of dilithium, you can stop directly when you value out of bound. In the mask case, it's a bit more complex. It depends a bit on your assumption. And it was discussed yesterday in a talk about the fact that maybe in mask form and in session protected form, then you want to verify the whole vector before putting which coefficient is actually not passing the test. So you have the two strategies. The early abort strategy, you just apply what I just said on every coefficient. If one is out of bound, you stop directly. But the good news is that for the no abort strategy, I mean, it's just, you just test everything, but you don't unmask. You don't unmask at the end, you don't perform the 0 test at each step, but you multiply with the previous result that you had. And so if one of them at some point is a 0, the whole product will be 0, and then the 0 test will detect it. So the two approaches are possible, and of course one is twice as fast as the other because in average you stop at the middle of the vector. So those techniques were implemented, and these are basically the results. So I compare with a previous technique that was similar, and we see that it's roughly twice as fast for the conversion. The main reason for that is that what really changed is the size of the modulus that we have. Before we had to go to 64-bit values, and now we can use 32-bit values. So on a microcontroller, you can hope that it's roughly twice as fast. I know you cannot say things just like this, but the idea is that you use a smaller value, so you have less computations to do down the line. And for rejection sampling, we compare to a technique from the previous paper, masking dilithium, and basically I think that the technique itself is just more powerful, so you have gain in every cases. Yeah, I should mention that this was C code run on the Cortex M4 without optimization, so there is still work to do if we want to know exactly what we gained there, but this is just a proof of concept. No abort versus early abort. So of course the results are similar. One is twice as fast as the other, but what we were gaining on one coefficient, we gain it also on multiple coefficients. And it's kind of obvious, but we tested still to be sure that everything was as we expected there. And the last thing I want to talk about is that in MLDSA, maybe one of the main difference for side channel is the deterministic versus randomized discussion. So in dilithium, in the randomized version, you can just pick your y's at random, and it doesn't matter, you just pick things one by one. While in MLDSA, it's kind of forced by the standard to go through the hash function. Which means for the masked version, then you actually have to mask the hash function and to look at the masked output of the hash function. So yeah, basically, there is no new masking technique required except that you have to mask the hash function, and we wanted to know approximately what we lose or what we gained here. And so these are the results that we had for this. We tried both approaches, and okay, it depends on the masking order, but we can say that it's around a factor 10 slower. However, this slide, which is my last slide. If you look at so this is for the sampling of Y. If you look in the full table, basically the weight of every algorithm, every procedure, you see that the sample of Y is quite cheap if you compare to decompose and the rejection, which is nice. But okay, if you multiply by 10, then it's become big also, but we don't expect that it will destroy completely the efficiency of the scheme. And so the last line is a comparison with one of our previous work. So we don't compare to the most efficient work because we don't have access to the code, but one of our previous work that was basically with the same kind of programming skills and masking techniques. So this is all for me. Thanks for your attention.
Thank you. Any questions? I have one question. Have you done practical evaluation of your technique?
I don't like this question. No,
we are
okay.
at CHES.
Yeah. Okay. No. So the thing is that the code is the C code run on a microcontroller. It's not optimized and it's probably leaking. I don't doubt it.
Okay.
The thing is that I feel like it's very hard in a paper to have everything from the design to the secure implementation. And sometimes people go one step further than us, which is doing the assembly optimization, but then maybe it's leaking. But so, yeah, I mean, I feel like we should to look at the design first and then to try to do secure implementation, but it's hard to do everything in one paper, well, depending on how many people are working on it. But
okay.
in our case, it's not.
Thank you. Any more questions? If not, let's thank the speaker again. And then we move to the second paper in the session. Which is masking. Oh, sorry. Can you
All right.
go back? Okay.
There is no laser pointer, right?
No.
Okay. That makes it more fun.
Which is masking floating point multiplication hardware for side channel attacks, and the presentation will begin by Aydin Ayzu.
All right. Welcome, everyone. Are you able to hear me all the way at the back? Awesome. So this paper is on masking as well, masking of a post-quantum crypto scheme. Unfortunately, the first author, my PhD student, was not able to make it due to visa issues, so I'm here to present it for you. So, does this work? Okay. Bottom line up front. So for those who are in a rush to attend to another meeting, I have just 1 minute to summarize this whole work. So in this paper, we propose the first hardware masking for the floating point multiplication, which can be used in Falcon as well as in other algorithms. This is not just applicable to Falcon, but also it can be used in the context of AI/ML applications. We propose a parametric hardware that can work on different floating point precisions, although the Falcon algorithm uses double precision, so our hardware is tuned for that. This thing is not working. Okay, we propose some novel subcircuits. The gadgets themselves are not novel, but the composition of them would create novel solutions that will help mask Falcon. We did do security testing in hardware with empirical evidence, as well as the proofs. I'm not going to show you any proofs today. You are going to have to look at the paper to get those proofs. And indeed, the overheads are high. The overheads are perhaps high in terms of absolute numbers, but they are also relatively high when you look at masking of other post-quantum crypto algorithms. However, I would urge you to not complain about the overheads in this session. If you want to complain about overheads, I'm chairing a session later today on homomorphic encryption. You are welcome to attend to that one. So, to give you a proper introduction, floating point multiplication has been targeted recently with side channel attacks. You know that the classical algorithms, AES, RSA, DSA, whatever, They do not use floating point operations. That's why it has been omitted for a very long time. However, we see that Falcon algorithm is using floating point multiplications, and Falcon has been chosen by NIST to be a standard. And the reason it was chosen was due to the small signature sizes, which make Falcon useful for embedded applications. And in embedded applications, we know that side channels are of primary concern. Also, there are emerging attacks on AI ML algorithms that can steal weights. So in that context, floating point is also used. So that's why it's also another issue that we need to solve. And the bottom line is we need to come up with effective techniques to prevent side channel leakage of floating point operations, and in particular, floating point multiplication. You all know what side channels are. You have a secret and a public value, and there is some intermediate computation that leaks Hamming weight or Hamming distance. And if you have enough measurements, you will eventually figure out the secret key. And the way to protect, there are several ways to protect against side channel vulnerability, and our favorite one is masking. So we used masking in this work to protect against these intermediate leakages. And the idea is to split the sensitive variables into multiple shares and then to compute on those shares instead of computing on the original values. So this way we can, we do not prevent, in a way, the leakage, but we make leakage statistically less significant to any fixed values in hardware. We also ensure that whatever output we have for any given input should be correct. So that when you, for example, if you mask A plus B and you get C, and when in the mask version, when you have the two masked outputs, C0, C1, when you add them together, you should get the correct result, right? And yes, there are two different techniques to do mask, two main techniques, Boolean and arithmetic share, and you need to decide which one you would use to make your hardware more efficient, and you need to convert between the two if needed. Right. So the next few slides are here to kind of justify the high overheads of masking that we have in this work. The figure that you see at the top is the baseline multiplication, which is not protected against side channels, and the one below is the secure masked multiplier gadget. And as you can see, there are a lot more computations at the bottom, right? So multiplications are now quadrupled, and you have some adders and subtractors. So that's why the nonlinear operations, the area overhead blows in correlation to the number of nonlinear operations. But this is not just that, right? So in hardware, you can have glitches, and glitches are known to leak information. So that's why you also need to add some registers to prevent those glitches, which will increase the overheads a little bit more. Well, but this is not just that. So now if you want to compose these gadgets randomly in any order and maybe get the output back into the input and so on, so you need to have a composable security. And to ensure composable security, you now also need to add a refresher at the input as well as another set of registers. Well, this is not just it. Now also you need to create extra random numbers, so the overhead gets more and more. And finally, you need to have secure conversion between arithmetic versus Boolean shares, so the whole thing gets more and more expensive, okay? So what about Falcon? So here is the simplified version of the floating point multiplication in Falcon algorithm. You also have exponent parts and the sign computation, but the figure here just reflects the mantissa multiplier part, where you need to start with the two inputs, 53 bits, and you have a multiplier there. And then after that, you have to go through a zero check operation, some Boolean computations on it, and finally choose the mantissa based on if there is a zero check or not. This computation follows the IEEE standard closely. Some operations are omitted, so it's a simplified version of IEEE standard. The computations are not performed on the modulo field, so you need to figure out a way to do that, because masking is by default defined on the modulo computations. And there are a bunch of compute units like integer multiplications, logical shifts, and so on. So one challenge in masking this computation is due to the large integer multiplier. You have 53 by 53 multiplier, and you have 4 of them, right? Because the mask gadget you see on the top right shows the full scheme. So one issue here is that this is an integer multiplier, right? So to mask this, the output should have the same size as the input, so it now becomes a 106-bit multiplier. And if you do this carelessly, if you just use a multiply sign in Verilog and just let the synthesizer synthesize whatever it wants, you will get around 35 DSPs. You have 4 of them, so if you do it carelessly, in the worst case, you would need 140 DSP units to mask a floating point multiplication. Moreover, you will have a randomness needs of over 1,000 bits, and due to this internally cascaded DSP units, you may have some glitches which may leak information. So you cannot do this trivially, and you need to figure out a way to do this in a more efficient manner. What do we do in unmasked regular computations? We have this, for example, schoolbook method where we can resize the operands according to the DSP sizes, and in particular here for the Xilinx FPGA, and then you can create these partial products and then add them up, right? So you will create, for example, one partial product at a time, and then you can do it sequentially, so you can have fewer DSPs in your hardware and do the partial product generation. However, the challenge for our case is when you mask this, then you cannot use DSPs efficiently because the output size, again, must be equal to the input size in the finite field. So one issue is which operand size we would use and how do we divide these computations into smaller chunks. So we use 8-bit chunks, but here just to simply describe another problem, I'll use an example where the original input is 8 bits. So you have, for example, 33 by 22 multiplication, and you want to resize them into smaller units of 4 bits. This would work in the unmasked domain, but when you start masking it, there comes a problem. The problem is due to the partial product addition and the carry bits that are created along the way. So in this example, let's assume, for example, that the value 3 is split into 2 shares, 2 and 1. So each of these within each square, so within the brackets, you see two masked shares. For the top, let's say 3 is split into 2 and 1, and let's say 2 is split into 10 and 8. So 10 and 8, when you add them, you have 18 modulo 16, it's equal to 2. So what happens here is that due to the carry bits that are generated in the partial products, and the carry bits must be accumulated later on, the output can be distorted. And what you do on the left is actually not equal to when you add the two mask output with the masking scheme. So you have to figure out a way to detect those carry bits propagations in the partial product, and then be able to rectify this. What we did in this case, for example, in this scenario, what you need to do is you need to look at both of the shares, right? You need to take both shares, figure out if there is a carry that's going to propagate, and then subtract that from the next partial product generation. But the problem is you cannot look both shares at the same time, right? So that will be combining the shares. So you need to detect these carry bits in a masked fashion. Hence, we built a masked carry bit detector that will keep the shares in the arithmetic domain and still calculate the carry bit. So it's a carry bit calculator gadget that works in the Boolean domain without a need for conversion from arithmetic to Boolean domain of the carry of the inputs. So one issue with this approach is you need to do this sequentially for all the partial products. Well, that's how we did in our first design, which makes this process takes a lot of time. So as a result, the computation, the latency goes higher and the throughput goes lower. For this talk, I'll be sticking to our sequentialized design, but in the paper, we do a design space analysis, and we show how to parallelize this computation to achieve a lower latency and higher throughput hardware. So this puts everything together. So the first multipliers that will be doing computations in smaller chunks, secure carry bit calculator gadgets, and then the rectifier circuit at the end that will subtract in case there is a carry bit that's generated. So the whole integer multiplication mask circuit will require 32-bit randomness, which is very good. And the utilization of DSPs are much more efficient compared to a baseline design, and it avoids arithmetic to Boolean computation. So this is more efficient. Thanks to our set of optimizations, this become more efficient when you compare it to other solutions. So what I described so far was all this part. The first part where you just do the multiplication of the mantissa. Then you have a sequence of other operations such as zero checks, Boolean, and mantissa selection. But all these operations are on Boolean domain, so they can be handled with Boolean masking. And that's what we do. We just take this whole design and use HPC1 gadgets to implement the Boolean masking in hardware. These will do, the zero check part will be done sequentially, but the rest essentially preserves the same structure. And the final multiplexer will only require 4 logical gates. So let me move on to implementation results first, and then I will conclude with the side channel part. So as I mentioned in the beginning, hardware masking is high. The unprotected design you see in the first row here, with the number of cycles needed to compute operations will be much higher when you go to the protected design. So the second row here is our sequentialized hardware that computes 1 carry bit at a time, and that would require 440x times more latency, right? So that's not very good. So that's why we describe in the paper a way to parallelize the carry bit calculation gadget so that the latency overhead drops down to 12x. And 12x is reasonable to some extent because the talk after this one will describe a software-based masking of the floating point, which again has a similar performance overheads plus some first-order leakages. Also, we have a high-performance protected design. We didn't implement this fully. This is based on estimations. The performance overhead in that case will be doubled, but the area overhead is now much higher compared to a baseline design. So for the leakage assessment, we use the standard TVLA methodology. I'll not describe the TVLA, but it's essentially, it doesn't prove that there is a leakage or not. It just gives you a statistical evidence that whether there is a leakage, whether a generic leakage. We performed these experiments on Sakura X FPGA board with a picoscope oscilloscope that takes 10 samples per clock cycle. And we use the standard randomness on, randomness off technique to mask versus unmask the design and compute our TVLA scores. We used up to 10 million traces in these tests, and each trace will contain up to 170K samples, so it's actually very long. And for TVLA, we use the first order and the second order tests. So here are some of the results. To summarize the results, what is supposed to leak does leak, and what isn't supposed to leak doesn't leak. The figure on the top left here shows the first order attack on our mask circuit with 10 million measurements. I'll say that some of these points get very close to 4.5, but our hypothesis is that they are false positives, and this is due to having a very long trace, again, 170K samples per trace. When we do the second order attack on the mask design, we see significant leakages that significantly crosses the threshold. And when we turn the randomness off and do the first order attack on the unmasked design, even with a few, so the top right figure is shown with only 5,000 measurements. So even when you use a few thousand measurements, the design starts to leak. And when you turn the randomness on, even if you have 10 million traces, then the design is secure. The bottom right figure here shows the first order fixed versus fixed test. You may ask why we did a fixed versus fixed test. Because in floating point, you have these corner cases, like 0 checks. And if you do a random fixed versus random test, you may not get sufficient samples from those corner cases. So to test those corner cases, we have applied the fixed versus fixed test, and we again see that when you mask, nothing leaks. The bottom left two figures are the balanced design, which are more parallelized, and we have the same story there. So when you turn the randomness on, first order masking will not succeed, but when you turn the randomness off and make the design unmasked, then you have first order attacks that are succeeding. So I will wrap up with the first slide that I have. This paper has shown the first hardware masking technique tuned for the floating point operations. Yes, it can be used in Falcon, but I believe it extends beyond Falcon as well for future lattice crypto algorithms and for AI hardware. This is a parametric solution that can support different precisions. We claim novelties in the building of the certain subroutines within the hardware, and we tested security and functionality. So I'm going to end with the overheads. Yes, we know that the overheads are high, and this is the first mask solution in hardware. Probably give it a decade or so, it's going to get lower. Right. With that, I'll conclude, and I'll be happy to have your questions. Thanks very much.
I don't think this mic is on. Do you hear me now? Yes, okay. Any questions? Please come to the mic.
Oh, the hard question is coming.
Hi, thank you for a very nice talk. You had a table that.
It's not working.
It's on? Okay. Yeah, so you had a table with the results for different types of designs that you have, the serialized, the balanced, the high performance. How about the randomness required? Does that change based on the designs, and what randomness requirements do you have?
It does. Low area required needs 32 bits. It's higher for the other designs. I'm not sure if I have the exact number, but it's not 1,000 bits, so it's the order of 100 bits. And in the paper, we have this randomness, not just randomness results, but the breakdown of randomness to support different gadgets.
Thank you.
Any other questions? Maybe I can ask one. For the area overhead, we understood it's very high, but do you have any ideas how can you optimize on this?
Well, you're going to have to wait for next year's CHES. Well, I mean, obviously there are things you can do. So we didn't explore we have some design space exploration, but we do not ever claim that it's an exhaustive design space exploration. We are not 100% sure if there are, if we did the right trade-offs in arithmetic versus Boolean. So you can definitely check the gadgets and see if there are different arithmetic versus Boolean optimizations available. And also the gadgets that we use HPC1, right? So I'm not claiming that's the best one available. So there are, every other few months there's a new gadget. So you can explore how using different gadgets will change the design, as well as play around with the parallelization and whether you do things in arithmetic versus Boolean. So
Okay, thank you. Thanks again. If no more questions. And then, okay. We have one more paper to be presented at this session. Yes. It will be on masking floating point number multiplication and addition of Falcon, and it will be presented by, I didn't see you before the session.
Can Chen?
Okay, thank you.
Yes, thanks for the introduction. I'm Can Chen, and I'm glad to be here to present our recent work, masking floating point number multiplication and addition of Falcon. And this is a joint work with Professor Junpeng Chen. Okay, and here's a table of contents today, and let me start with the introduction. Okay, the story begins. I'm sure you're all familiar with that. To defend against potential threat from large-scale quantum computing, the National Institute of Standards and Technology in US, also called NIST, initiated a standardization process for bosonic cryptography in 2016. And 6 years later, Falcon became one of the SATI schemes that we expect to be part of NIST standards in the future. And theoretically, this algorithm can basically security on some hard mathematical problems that are considered still hard, even with quantum computing. But in practice, when these algorithms are run by computer programs, they may suffer session attacks. And here's a rough diagram of Falcon's sign algorithm. And as you can see from the left, the message M and random source R are first sent to a hash function. And then they go through a faithful transform, and then pass all functions, and finally output a signature vector S. And in the middle, there are two colored boxes, the red one and the green one. These are places where a secret key plays a role there, which also implies session attacks could happen there. The green one, which we call Gaussian temporal over lattices, there are already session attacks, and potentially there are also corresponding countermeasures to mitigate the threat. But for the red one, which we call the print vector computation, there are session attacks, but there was no countermeasure until our work. So our goal is simple. We want to fill in the upper right cell with our paper. Our contribution is the first masking scheme on the print vector computation as a countermeasure against current session attacks on Falcon. Oh, and to give some notation for today's talk, we assume that for variable x, its jth bit is written in the superscript, and the ith bit to the jth bit of a variable x is represented as j:(i) in the superscript. And a sequence of n variables is written as xi with 1 less than or equal to I less than or equal to n in the subscript, or simply just xi. And for proposition P, we use double predicate to represent its evaluation. It's 1 if and only if the proposition P is true, and 0 if otherwise. And okay, let me give some preliminaries for better introduce our work. The first, Falcon. Falcon consists of 3 main algorithms: keygen, sign, and verify. In keygen, the secret key and public key were generated, where the secret key are essentially 4 short polynomials, small f, small g, big F, big G. They are all of degree less than n and integer coefficients, such that small f times big G minus small g times big F is a prime number Q. And the secret matrix B is formed by these 4 polynomials. And the public key is a polynomial H, which is equal to GF inverse modulo prime number Q. And the public matrix A is formed by a constant polynomial 1 and polynomial H. And you can check that BA is equal to 0 modulo Q. And to sign a message M, a short signature vector S is generated such that SA is H of R and modulo Q, where H is the hash function and R is the random sort. And to verify message M with signature S, we simply check whether S is short and SA is indeed H of R and modulo Q. So the key step is in sign algorithm how to generate this short signature S. And to do so, one first computes the polynomial C, which is H of Rn, and then find the solution both C vector, which is polynomial C and 0 polynomial, such that CA is H of I modulo Q. But C is not short So we then find the parameter vector t, which is CB inverse, and then apply the nearest span algorithm to find a vector z such that t minus z times b is a zero vector. And now this zero vector is the signature S. And note that this S times A is really equal to h of r modulo q. And here we mark the third step red because this is where sexual attacks had happened, and this is a problem we want to address in our paper. So now we introduce form-fitting number arithmetic and why it's related to our problem. Well, the parameter vector computation, if you expand the formula, includes polynomial multiplication. The parameter vector t is equal to 1 over q times c dot minus big F and c dot small f. These are all polynomial multiplications. And to see about the whole process, the parameter vector computation is performed after Fourier transforms, which means all the polynomials above are performing multiplication after Fourier transforms, and polynomial multiplication will become coefficient-wise complex number multiplication after Fourier transforms. This is essentially what parameter vector computation does. And recall that a complex number is represented by two 64-bit formal numbers, is real part and imaginary part. So for parameter vector computations are complex number multiplications, and complex number multiplications are formal number multiplication and additions. And recall that a formal number is composed of a sign bit, 11-bit exponent, and 52-bit mantissa. And its representative value is given by the following formula. Okay, let me briefly recall how formal number multiplication and addition works. For formal number multiplication, we first XOR the sign bit of the both operands and add the exponent, and then do the multiplication. After multiplication, the mantissa product can be very large, so we first redshift the result, and then we pack the sign bit exponent and mantissa and perform proper rounding. The last step is called FPR in Falcon's submission code. For phonical number addition, one first make sure the first operand is larger than or equal to the other, the second one, and then we redshift the second operand until the exponent of both operands match together, and when they match, we can do the addition or subtraction. And after addition or subtraction, we normalize the result to a proper range, and just like the multiplication case, we pack the results and perform proper rounding by a subroutine FPR. Now, the last masking, I'm sure you're all familiar with that, but let me just briefly recall it. Masking is an effective way to resist sexual text, and its main idea is to secret share all the secret variables. There are two common types of masking. The first one is Boolean masking, where a variable x is split into n shares, x1, x2 to xn, such that the original x is the XOR of all the xi shares. And there's arithmetic masking, where a variable x is split into n shares, such that x is the sum of all the shares. And in each round, all the xi are freshly randomized, and all the operations now go with share-wise operations, so that any single intermediate value will not be independent of the original secret value. Okay, then let's go to our main approach. First, I will give a brief overview. And we know that an intuitive approach to masking algorithm is for operations like bitwise AND and bitwise XOR, we just use Boolean masking because it's easier to do so. And for operations like addition or time, we use arithmetic masking because it's easier. And if necessary, we apply the following gadgets, which are A to B, arithmetic to Boolean, it maps an arithmetic max variable to Boolean max variable, and B to A, which maps a Boolean max variable to an arithmetic max variable. Okay, but we found that some operations in formal number arithmetic cannot be easily implemented by the web above, including check whether a secret value is 0 or not. This is not easily implemented or not easily seen how to do so by the approach above. And redshift the secret value by another secret value. And finally, normalize the secret value to the range between 2 to the 63rd and 2 to the 64th. And I mean to left shift the secret value, left shift keep shifting it until its range is in 2 to the 63rd and 2 to the 64th, and we stop the shifting. These three operations are not easy thing how to do. So we design number gadgets for it, including secure non-zero, which securely check whether a value is 0 or not, and secure floating point assigned redshift, which securely redshifting a secure value by another secure value. And finally, secure floating point normalization, which normalize a secure value to the range between 2 to the 63rd and 2 to the 64th in a max way. And we also make several improvements. And now I will sequentially introduce our three number gadgets. The first one is secure non-zero. And secure non-zero, its goal is to output 1-bit shares be given shares x, such that, well, the original x is 0 or not, its evaluation is the XOR of all the BH shares. And we first look at the left one, the Boolean max case. For Boolean shares, our method is simple. We just OR all the bits together, which means a value x is 0 or not, if and only if all the k bits ORing together is 0. So now we just OR all the bits of x, and then we need a secure OR operation. And this can be constructed by applying a De Morgan's law and a secure AND gadget. Secure AND gadget has been proposed and developed by many previous incredible works. So yeah, that's the Boolean shared version secure non-zero. And for arithmetic shared version secure non-zero, and a simple way is to apply n shared A to B, and then we use Boolean shared version secure non-zero to do so. But instead of doing this, we consider that the sum of all xi is 0 if only if the first n over 2 shares XOR the negative of the last n over 2 shares is 0. Using this relation, we can use two n over 2 shares A to B on the first n over 2 shares of x and the last n over 2 shares. And then we apply the Boolean version secure non-zero. This is how we construct the arithmetic version secure non-zero. And in this way, we replace one n shared A to B with two n over 2 shared A to Bs. And in most designs of A to B, this is a good deal. It will be more efficient. Now let's go to secure floating point redshift. Its goal is given 64-bit shares X and 6-bit shares C. We need to derive new shares Z such that Z is X shifted by C bits. And to do so, we observe that right shifting and right rotating are very similar. Right shifting and right rotating by a value C only differ by their most significant bits of the result. But right rotating X by a value C is equal to right rotating X by C modulo 64. And this property is what right shifting doesn't have. So using this property, our idea is to right rotate all the xi's by C1, C2 down to Cn sequentially. And then we transform the rotation result to the shifting result. Now, some rotated high bits are redundant, so we use an index n, which is equal to 1 and 63 zeros in expanded representation to indicate the first meaningful bit of the result. To do so, consider the value m shifted by c bits in expanded representation is equal to c zeros, a 1, and the rest of bits are 0. And use this value, we can construct another value m prime, which is equal to c zeros, and all the rest of bits are 1s in expanded representation. And then by an AND operation with this m prime, we can clear all the USS bits and get the desired shifted result from rotated result. This is how we do the floating number assigned redshift. And for floating number normalization, its goal is given 64-bit shares X and 16-bit shares E, we need to derive shares X prime and E prime, such that X prime is X shifted by C bits and E prime is E subtracted by C, where C is the smallest integer such that when X is shifted by C bits is in the range between 2 to the 63rd and 2 to the 64th. And our idea is to repeatedly check whether the 64th bit of X is 0 or not by our secure zero check gadget. And if it's 0, then we shift it by 1 bit and subtract it by 1. And if it's not 0, then we don't shift it and we don't decrease E. And to prove efficiency, we don't check one bit at a time. We sequentially check a number of power of 2 bits at a time. Okay, to wrap up, utilizing these 3 gadgets, we designed the following gadgets, including secure FPR. It's a secure floating point number packing and rounding by masking, and secure floating point multiplication and secure floating point addition. And we leave the details of the implementations and several tricks for improvements in our paper. Now let's go to the evaluation of our design, including security and performance. The first security, for theoretical security, we consider the program model. Well, given a positive integer t, the t-program model assumes that there's an adversary. He's able to pick any t-intermediate values in the algorithm. And know that to be secure in the t-program model, the number of shares must be larger than or equal to t plus 1, and any share cannot be combined with each other in the algorithm. And it can be complicated to prove t-program security directly for a large composition of gadgets, so we turn to another concept of non-interference. A gadget is called T-non-interference or TNI secure if every set of t-intermediate values can be simulated by no more than t shares of each of its inputs. And there's a stronger definition called T-strong non-interference or TSNI. A gadget is TSNI secure if every set of Ti intermediate values and TO output shares, they can all be simulated by no more than Ti shares of each of the inputs. So if a gadget is TSNI secure, then we can use less number of shares to simulate the probe values than a TNI gadget. So if T is n-1, and if a gadget is TNI or TSNI secure, and if any n-1 input shares are uniformly and independently distributed, then it's t-program secure. And all the gadgets in our paper are proven either TNI or TSNI secure. And I'm not going to go through the details of the proof because it can take too much time. And for practical security, we conduct the text vector tissue assessment or TVLA. And let me just briefly recall how TVLA works. In TVLA, experiment 1 records 2 sets of power or electromagnetic traces where the first set is given by running the program with a fixed input, and the second set is given by running the program with random inputs. Then we apply the electricity test to see whether there's significant difference between the 2 sets. And by convention, we consider leakage significant if the t value exceeds the 4.5 threshold. And for very long traces, we refer to Dean and his team's work to alter this threshold to avoid false positives. And here's the result of our TVLA. It's on floating point number multiplication. From the left to right are unprotected multiplication, our 2-share design, and our 2-share designs. And the red dotted lines are the 4.5 thresholds. And the green dotted lines in the right graph is the altered threshold. It's slightly larger than the 4.5 threshold. And you can see for unprotected ones, almost every point exceeds the threshold. But in our 2-share design, all the points are within the 4.5 threshold in 10,000 traces. And for our 3-share designs, almost all the points are within the 4.5 threshold, and every point is strictly within the altered threshold. And for floating point number addition, a similar situation happens. And now it's our performance. Here's the performance result when we run our algorithms on an ARM Cortex-M4 microprocessor. And for floating point number multiplication, for unprotected ones, it goes around 300 cycles in our environment. And for our 2-shared protected design and 3-shared design, it goes around 23 times and over 100 times cycles slower than the unprotected ones. And for floating point number addition, the 2-shared design goes around 35 cycles, and the 3-shared design goes around 100 times cycles. And this is pretty slow, so we look at the details of our design, and we found that for floating point number multiplication or floating point number addition, the A to B gadget, the secure FPR gadget, and the secure A gadgets, these 3 gadgets are the main reason, the main bottlenecks for our performance. They take up the most number of cycles. And also, we found that secure FPR, why it's so low, is because it uses two 64-bit secure add in our design. So the main bottleneck of our performance is the A to B gadget and secure gadgets. Okay, then I'll make a short conclusion for today's talk. In this paper, we present the first matching scheme on functional number multiplication addition to protect the primitive computation against current section attacks. And we design our gadgets, secure non-zero, secure unsigned redshift, and secure normalization to do so. And our gadgets are proven TNI or TSNI secure, and the TVA results show no leakage in two-shared design in 10,000 traces, and no leakage in the three-shared design in 100,000 traces. And finally, our countermeasure, when compared to the unprotected ones, is quite slow. And we found improved designs of secure add and A to B gadgets can further reduce the cost because they are the bottlenecks of our design. Yeah, and thank you for your attention. I'm happy to answer any question.
Thank you. Any questions? Can you briefly
Yes.
compare with the previous paper your results?
Yes, I think the main difference is that our design is software-based, and I think their design is hardware-based. And also, our design can be extended to high order, and they focus on the first order security, and also we do the functional number addition, and they focus on the functional number multiplication case. Yeah, I guess these are the differences.
Okay, thank you. Any more questions? If not, let's thank all the speakers of the session. Thank you.
Thanks.